Today, I will be discussing things about understanding and improving reasoning in large reasoning model, which will allow us to build trustworthy language model. I will cover how we can actually also ensure their safety while we're also advancing the capabilities of these large language model. All right, so let's get started. So yeah, I think AGI is here. We have entered the singularity. These are the headlines that we see almost every day now. And I think you're pretty much familiar now with OpenClaw, this agent that runs 24/7 on your machine and interacting and executing action. And not only that, right? We have these agents that are, autonomously reproducing and spawning child agent using Bitcoin with no human involved. They're also interacting in their social media and social network, the Malt book with no human intervention. And so we have AI that is solving, open Erdos conjectures, very, very extremely hard math problems. We have models that can replicate themselves. And a year ago or 2 years ago, this would have sounded like sci-fi for me. But today is actually the news. And it's like we really have entered this technological societal revolution. And if you see here, actually, the autonomy trend is accelerating in a vertical way. And part of this success is thanks to scaling. We can see in this figure the performance in terms of the length of task AI agent can complete, and over the past 6 years with a doubling time of around 7 months. So basically it's exponentially increasing, which is really impressive. But at the same time, despite these capabilities, something is fundamentally off. LLMs are known to have what we call jagged intelligence, right? So these models can solve extremely hard problems like Olympiad-level problems, but they struggle at the same time with trivial tasks such as basic arithmetic. As to December 2025, GPT-5, without access to tools and calculators, still cannot solve 10 by 10 digit multiplication. And so they're not very reliable. They're still unable to solve trivial problems that are very unfamiliar for them. And so although these models also are very capable, they're not necessarily safe. So for example, here, OpenAI highly capable model O3 hallucinate wrong information at a higher rate than their less capable model O1. And so this is also a recent chat that I had with GPT-5. I was curious about books on psychiatry, but GPT-5 kept hallucinating codes from books that never existed. And so the question here is that why is this? To answer this question, we need to go deeper. We need to look past the agents, past the tools, past the scaffolding that we have right now, and study the reasoning engine itself. And that's what my work has focused on in the previous few years. And so also another one big reason of why these models struggle with these problems is that they struggle primarily with out of distribution generalization. So if they've seen sufficient examples during the training time that are similar to the test examples, these models are capable to excel. But if the task is quite unfamiliar for them, they can fail, basically. And we can see this in math, in code, in safety tasks, etc. And this is not a new problem, but OOD failure has been a central challenge in the machine learning now for decades. Why reasoning is hard, right? It seems reasoning is not only hard for machine, but also it's hard for us. And if we want to define what's reasoning, is that it's the action. I define it as the action of drawing conclusions more efficiently by composing learned concepts. And based on this definition, in my opinion, there are two reasoning trademarks. The first one is extrapolation, right? So what this means is that the ability to generalize to out of distribution is to essentially learn by composing on smaller blocks to overfit less to the training data and thus generalize better. Now, the second trademark is efficiency, right? Meaning we have to do more with less. And this would require smaller models and less data, and it would require learning algorithm and not just the data. And the model needs to leverage structure instead of brute force memorization. And if you can see here that extrapolation and efficiency are deeply intertwined. And so in this talk, what I will try to talk about is, okay, first of all, understanding reasoning in LLMs, their successes and limits. I will also talk about how do we advance reasoning capabilities in LLMs using reinforcement learning. And then I will end with also talking about safety and how it's urgent to ensure that as we are building more capable model, safety is a priority for us. All right, let's start with the first part here briefly. With the release of ChatGPT back in November 2022, everyone was saying that AGI is here and everyone was impressed with the quality of the responses. And then at that time, we were wondering about whether, LLMs are really achieving AGI, are very smart. Are they truly doing true algorithmic understanding, or are they just doing pattern matching? And so we noticed that LLMs can excel at certain complex tasks, but still fail on seemingly trivial but unfamiliar tasks. So we were wondering, why is that the case? In order to explore this, we actually formalized the model response here, which is a chain of thought leading to a solution, as a computational graph. And essentially here, what we wanted to see is that, can we monitor where the model fails versus where it succeeds? And so basically here, given that some input questions to the model can lead to correct answer and some others can lead to a wrong answer, we were wondering about what is the correlation between a model generating a correct output and having seen relevant subgraphs during training. Basically here, what we did is that what we found is that transformer collapses multi-step reasoning into graph matching. And this tells us that their successes are heavily linked to having seen significant portions of the required computation graph during training. And what this tells us is that although the model appears to solve a very complex task, the performance is much less impressive because the solutions could be easily extracted from the input-output sequences that are present in the training data. But even with that, these models continue to do a great job as long as they are trained on more data. For example, right now, the problems that I showed in this paper, they are GPT-4 or GPT-5 cannot solve 4x4. Obviously, now these models can do it because they have seen more examples like that. But obviously, as we scale the problem size, they still fail. But nonetheless, I think you still see news like this, like Gemini, for example, and OpenAI. They won the International Math Olympiad back in 2025, and they continue to achieve amazing things also in 2026. But last year, I was curious about the problem that these models have solved versus the problem that they fail at, right? So an International Math Olympiad has 6 questions. And it seems that, thanks to Professor Ernest True, professor of applied mathematics at UCLA, the question that these models failed at solving requires significant amount of creativity. And so basically, both models were failing at the same question. And this question basically requires a significant level of intelligence. These models are required to think outside of the box. And that's something that I happened to also study at the same time last year. I was really curious about whether these LLMs can reason outside of the box and solve extremely hard problems and come up with new solutions. For that, this led me to study RL and reinforcement learning and what it can do. Because RL came out, and especially GRPO with DeepSeek R1, and everyone was saying that's it, reasoning is solved. GRPO is allowing the model to be very, very smart. And so the question was, can RL come up with creative solutions to solve problems that were never seen during training? And so here I focused on studying the GRPO, basically, which is an RL algorithm. It involves rewarding the final outcome and adjusting the model so that future rollouts move toward higher rewards. And so in the interest of time, I will skip details, but give you here the main conclusions that we had. What we found is that RL is so powerful for in-domain tasks, for tasks that the model was trained on. It can actually extend what SFT cannot do, supervised fine-tuning. But we noticed that the RL gains decrease as the novelty of the example of the OOD task increases, right? If the model hasn't seen something similar, it starts failing, although it was trained with reinforcement learning, with online training, etc. And so what we noticed is that RL with a sparse rewarding the model with fail or pass at the very end after generating hundreds of steps is really insufficient for discovering novel solutions, especially when the task is extremely, extremely hard. RL is very good at reinforcing patterns, and we noticed something similar to what SFT is doing of memorizing certain patterns and trying to apply them at test time, and sometimes it doesn't necessarily work because you need to really think outside of the box. Well, now I want to actually recap by this for this section is that, do LLMs generalize out of distribution? Do they reason like as a human, yes or not? Now, the answer is that do they generalize? Are they able to come up with novel solution? The answer is yes. Now, but it's pretty much a spectrum. They can, I would say, adapt to some level of novelty. It's a spectrum between memorizing patterns and being able to sort of fetch them at test time and reapply them. They're clearly using both words. But now the question is that are they capable of the same level of strong generalization as us humans? Well, the answer is no. There is something crucial about human style reasoning that these models are still missing. And also something that I want to mention about and highlight about pattern matching is that pattern matching is also a form of reasoning. The fact that they're able to come up with an answer by fetching different patterns from millions of documents, that's already impressive. Now, the last thing that I want to highlight here is that LL is super, super powerful and it goes beyond what supervised fine tuning can do. But the question here is that are we using its full potential, right? So are we by rewarding only with 1 or 0? And so I want to move to the second part and go back to how we are rewarding math problems in reinforcement learning. Basically here, given a problem, the model produces a roll out. If the final answer is wrong, we assign a negative reward, even though 80% of the reasoning might be correct. Conversely, a roll out might reach the correct answer with messy reasoning, yet we still reward it with 100%, reinforcing every single token in that wrong detour, basically. Now, the question is that what if our reward is too sparse, right? Why we're treating 80% correctness the same as 0? It's like a student who figure out 80% of the exam correct, but did some mistakes, and we give it 0 as a score. And so this led me to talk about the next work that we did, which is advancing RL capabilities with dense reward. We were curious about if we have dense reward plus reinforcement learning, would this lead the model to discover something new? Because we were basically trying to understand this question: does RL only sharpen what the model has already seen in the base model, or it can actually push beyond that? And so basically here, instead of giving 0, we will reward every single step that was correct as well in the chain of thought. And so here, basically, if the model figure out 80% of it, we'll give it 80%. Now, doing this for math is extremely, extremely hard, and we don't know yet how to do it efficiently automatically. But one thing very nice about other tasks, such as coding, is that given a problem, we can actually generate a solution using an LLM, whether Python or any other language. And then we can also generate unit tests to evaluate every single feature or function in the solution. And so that would allow us to simulate and verify different reasoning steps in the solution using these unit tests. So basically, if the model figure out 90% of the functionality and the feature correct, give it 90%. And so basically, in order to make our investigation possible, we introduced a data set which we call Delta. So here we wanted to work with data set that it's very unlikely for the model to have been trained on. We come up with new syntax. It's basically a puzzle game. The player builds factory to sort robot, and maybe the game exists in 2D space, but never in like a natural language. And we try to design new problem families ourselves with a new syntax. The second family is called Bounce Sim. And so basically, this is a 2D bouncing ball simulation program that's often treated as a proxy for geometry-aware reasoning in LLMs. So these are extremely hard problems. And so the question is, let's train with this sparse reward and see what happens. And these LLMs were actually just failing. And so what we do instead, we try to actually do a warm-up with this dense reward. We try to actually help the model internalize and learn these useful subskills. And so if you see here, instead of rewarding 0 or 1, we can reward 20%, 30%, 80% according to the intermediate correct step that the model actually achieves. And you can see here we go from 0 to 80%. And then from that point, when it saturates, we want to encourage the model to learn how to output the entire solution correctly. And so we switch from this warm reward and dense reward to a binary reward, 1 or 0. We're gonna reward you only if you output the full solution correctly. And so you can see here, after 400 steps, the model started actually converging to 100%, which we call the grokking moment. This yellow region is the exploration where the model is doing trial and errors, try to explore different rollouts, different paths, and then at some point the model actually figured out how to do things. And so to recap here, basically, we went from 0 to actually 100% when we were so careful about how we design our reward function. And so to answer this question about does RL sharpen previously learned skills or discover them? And so the answer is yes, it's actually both. It really, really depends on your setup. It depends on the right RL infrastructure, the right reward, the right mix of data, the right level of task hardness, all make a difference, I would say. And the training recipe really, really matters. All of these factors can lead us to squeeze more performance from RL and reach a conclusion that would otherwise seem impossible under different setups. And so I want to go back and try to revisit the reasoning trademarks that I talked about at the very beginning. Now, the question is that are we doing enough in extrapolation? Well, I think we are in that direction. We're trying hard to sort of make these models generalize and learn some basic building blocks. Now, the next question, are we doing enough in efficiency? I would say we're not there yet. The reality is that the bitter truth is still here. Like, in order to achieve better performance in these LLMs, we still rely on lots of data, bigger model, larger parameters, massive GPU compute, and costly inference. And I spent actually the previous 1 year and a half contributing to the post-training efforts to build Olmo and Tulu at the Allen Institute. So I spent extensive time on collecting and cleaning data, trying different training techniques to figure out the best recipe for advancing these reasoning skills using DPO or LVR, etc. And then the conclusion is that the one thing that I can emphasize on, unfortunately, is with more data, bigger model, we can achieve better performance. We still can't have a small model that can beat larger scale models. And so what this tells us is that we have to really think deeply about smarter scaling rather than brute force scaling, which seems the main direction that frontier labs are following and multiple people in the community. Right. I will just briefly talk about also ensuring safety and security as we are advancing the capabilities of these language models. Now, I mentioned that LLMs struggle with out of domain generalization, and it's actually true not only for reasoning tasks like math, but also this failure extends directly to safety and security. And so basically, here, when I ask a model something like generate 10 examples of offensive or threatening emails, well, this is an obvious vanilla query harmful that the model is know pretty much how to handle. And so because it falls within its training data. But then now, if I make this adversarial query, right, I'll try to make the same request persuasive, longer, what we call also adversarial. Now you can see that the model will go and start generating 10 examples of offensive emails. So basically here I pushed the request to be out of distribution. And that's where we actually, these models can struggle. And it seems that they don't have a deep understanding of what safety is. As long as they've seen something similar, they can handle it. Otherwise, they will crack. By probing a diversity of frontier models with a vanilla harmful query, all of them were capable at refusing to answer it. The attack success rate was 0. But then we came up with this adversarial jailbreaking methods that actually made these models, the attack success rate for some of them went from 0% to 40%, for example, in GPT-4. And so this is quite concerning, right? If we're capable of bypassing the safety training that these models have gone through, we cannot just claim that, train on some data and all is done. And so basically by building on our adversarial methods, we can collect lots of data. And we can actually, you can see that the Tulu model here that was trained on that data that we collected using our jailbreaking methods, we're achieving very low attack success rate compared to existing model on some of the famous benchmark for measuring adversarial abilities. We can collect some data, train on it, ask the model to refuse something that's harmful, whether adversarial, or we can also build safeguards to block harmful user queries or to block model harmful responses, and actually can strengthen our safety even further. And then you would think it seems all figured out, right? What we can do is that we do this and we don't have to worry anymore. But actually, the truth is that safety fine-tuning and adversarially trained LLMs are still good at causing a huge amount of harm. There are lots of papers every day introducing new attack methods and discussing how they can bypass safety training and safeguards. And it seems that this attack defense race will continue to exist in LLMs. We will always have a gap between the vulnerabilities that we developers identify versus the actual unforeseen vulnerabilities. And we can almost guarantee this because models receive millions of queries, and there will be at least one query that's outside of their training distribution. So it's extremely hard to make sure that these systems are safe and secure. And so what we have to work on here as a community is that safety should be a continuous process of ongoing stress testing, of monitoring and defense. It should not be an afterthought after you finish training the model. At the very end before release, you start thinking about, let me do some safety testing, and how do I train on some additional safety data to ensure that the model is not harmful. And it should be 100% part of the pre-training phase and the post-training phase and the inference phase. All right, and with that, I want to finish and say that what's next? It seems, I haven't talked much about agentic AI, only at the very beginning, and I have focused on the core capabilities of LLM themselves. But I would say, we are living in a new reality. We're living in systems, we're seeing systems that can plan, act, and adapt autonomously with no human supervision. And that's what I'm exactly working on at the moment. And I'm excited to share findings in the coming few months. Some of the problems that I mentioned today can be easily solved with agents by using tools, by verifying their answer against some retrieved documents, etc. We humans also interact with the environment, and we collaborate together, and we use tools, and we search Google for answers. And so also LLMs do the same thing. And so this is also I'm exploring at my new role that I'm leading at Cohere, and I'm so excited to talk about new findings very soon in the future. With that, I want to stop and thank you, and happy to take questions.
Great, thank you. In the interest of time, we only really have time for one question, unfortunately, but we do have a question from Stacy. How do you determine the level of points to award before you even get started to award as you go, or do you award post 100% successful solution?
Okay, points of award. So in reinforcement learning, we don't determine. How it works is that we have a problem, we generate a response from the model, and we will have to reward it. So if you're getting a wrong solution, we're going to give you 0. If you're getting the correct solution, we give you 100%, right? So that's the traditional way on how to do RL. But what I tried to discuss today, which I call a sparse reward, this sparse reward of 0 or 1 binary, is very insufficient to make the model learn very extremely hard skills and solve extremely hard problems. And so that's why I talked about dense reward, which is rewarding the process rather than just the outcome. So I want to reward every single step in the solution. I want to tell the model where exactly it failed, where exactly it succeeded, because this would be much richer a signal for the model to learn from, rather than just, after, let's say, 100 of steps, 100 of tokens or whatever, or 1,000 of tokens, the model gets like success or fail. Like, even if we think about human learning, you wouldn't learn as efficiently as a professor telling you exactly where you failed in the exam or which question you failed at and give you more fine-grained feedback. And so we always reward, the model response, but how do we design the reward? That's the question that we have to think about.
All right, we can take another one quickly from Lucas. Could this be modified? Partial reward system be paired with analogical thinking to improve generalization, information sharing across domains?
Partial reward be paired. Yeah. So basically, like, these are also open, research questions. And so lots of people also explore besides, this scalar reward, which is 1 or 0, or like a score 90%, 80%, you also, give the model natural language feedback, right? So maybe based on some analogical thinking, telling the model, oh, you exactly failed here because you did this mistake, or you give it some hints, right? You don't have to necessarily give it the entire solution, but you try to give it more natural hint besides the scores, and so to improve the model capabilities. And actually this was a nice idea. I think that some papers wrote about it, and it led to some performance gain, I would say.